So coming to the problem, here consider a two-span prismatic continuous beam as shown in the figure. Analyze the beam by using a slope deflection method. Given that a clockwise rotational slip is 0.002 radian, which is going to occur at the fixed end A, you're going to sketch the deflected shape and draw the bending moment diagram. And here you're going to assume EI to be 8 into 10 power 4 kilonewton meter square. So this is a given question. First, we'll see the sketch. So here in this sketch, we can see that A support has been rotated with a 0.002 radians, which is of a clockwise rotation. And here B is again an internal support. I mean, external support only, roller support. And another C support is a fixed support. And there is no loading for this problem. And here AB span is a 5 meters, BC span is a 3 meters. And here EI is a constant throughout the ABC beam. Coming to your first step, you're going to determine the degree of freedom. So for this problem, we can just see as it is a fixed support, it has been just rotated. So here you're having the rotation, but the translation will be equal to 0. Whereas coming to the B support, you are having a rotation, but you don't have any translation. At C support, both rotation and translation are equal to 0. And now here delta A is equal to 0, but theta A, there is 0.002 radian. Whereas at the B support, the theta is not equal to 0. That means rotation is there. But whereas delta B will be equal to 0. And at C support, both theta and delta are equal to 0. So here the degree of freedom will be equal to 1. So that is your theta B you are going to find out. So this is your step 1. Coming to your step 2, you're going to calculate the fixed end moments. So since there is no loading in this entire ABC beam, ABC span, so here the fixed end moments for all the spans will be equal to 0. AB, BA, BC and CB. And then your next step is you're going to write down the slope deflection equation. So this is your generalized slope deflection equation. So MAB will be equal to MFAB plus 2EI by L into 2 theta A plus theta B minus 3 delta by L. Here MFAB is your fixed end moment, whereas 2EI by L into 2 theta A plus theta B will be your moment due to the rotation. And this is minus 6EI delta by L square will be the rotation due to the settlement. Similar way, you're going to write for the BA moment also. And then since there is no settlement in this above problem, so I'm just substituting the delta will be equal to 0. So now by simplifying these two equations, you're going to get MAB will be equal to MFAB plus 2AI by L into 2 theta A plus theta B. Whereas MFBA also will be equal to MFBA plus 2AI by L into 2 theta B plus theta A. So now next you're going to use the slope deflection equations for the different spans, that is AB and BC. So now coming to your AB span. So AB, since here you can just see, since AB is not equal to 0, even though it is fixed. So here theta A is, one second, is not equal to 0. So theta A, it is given as 0.002 radian. So it has been just rotated. Okay. And then MAB will be, by substituting this entire thing, since there is no fixed end moment, it is 0. By substituting this entire thing, you are getting MAB will be equal to 128 plus 2EI into theta B by 5. Similarly, MBA also you are getting in the same manner. So this is an MBA equation. And then again for span BC, you are going to consider this equation. So since the support at C is fixed support, the theta C will be equal to 0. Therefore, MBC will be equal to this 4EI into theta B by 3. Similar way, MCB also. Then here we are just substituting in place of theta C as 0. And by simplifying, you are getting MBC and MCB values to be like this. Okay. Next, coming to your next step, we are going to use the equilibrium equation. So coming to this equilibrium equation, only you are having a joint at B only. Therefore, sigma MB will be equal to 0. So that means moment BA plus moment BC will be equal to 0. So this is a joint equilibrium condition. By substituting MBA moment and MBC moment, so the equation will become like this. So by solving this entire equation, you are going to get theta B will be equal to minus 0.000037. So this negative indicates that it is an anti-clockwise rotation. So here you are going to substitute the EI value also, which is already given in the question. And then we are going to draw the elastic curve. So since theta B, you got it as minus 0.00037. So the elastic curve will be equal to, so the elastic curve will be, so since there is a rotation at this, um, as it has been rotated to this clockwise, and at theta B, you are having a negative value. So this will be equal to, okay. So at A, you are having a clockwise rotation of 0.002 radian. At B, when we draw a tangent, you are having an anti-clockwise rotation of 0.00037 radian. At C, you are having the rotation has to be 0. So this is an elastic curve, what we have drawn for this above problem. And then coming to the calculation of your final end moments. So by substituting this theta B value in the slope deflection equations, so you are going to get MAB is a positive value of 116.16 and MBA is plus 40.32 and MBC is minus 40 kilonewton meter and MCB is minus 19.73 kilonewton meter. So again, by writing all these values, MAB plus 116.16 kilonewton meter, MBA is 40.32 kilonewton meter, MBC is minus 40 kilonewton meter, MCB is minus 19.73 kilonewton meter. So this is a final figure. So this is a given problem. So for this problem, we'll just draw the free body diagram. So this is A, this is B, and this is C. So MAB moment, you are getting it as positive. So that means it is a clockwise of 116.16 kilonewton meter. Again at BA, it is again positive. So it is also clockwise of 40 kilonewton meter. And BC, it is negative. So anti-clockwise of minus 40 kilonewton meter. And CB, again, it is negative. So that means, sorry, it is anti-clockwise of 19.73 kilonewton meter. So since there is no external load acting on it, so only for this moment, you are going to draw the bending moment diagram. Okay. So here it is in sagging nature. So sign convention once again. So if it is in sagging nature, positive. If it is in hogging nature, negative. So this is a sagging moment. And this is a hogging moment. So since it is sagging, it is of 116. So it is of 116 sagging. Again, it is a hogging of 40 kilonewton. So it is 40 kilonewton. So this is 116.16 kilonewton meter. This is 40. Again, here you are having a sagging of 90. So this is 19.73 kilonewton meter. This is C. and this is B of 40 kilonewton meter. So this is B and this is A. So when we draw the figure, okay, so this is plus, this is negative, and this is positive. So this is your final bending moment diagram. So you can just, as there is no loading, external loading acting on it. So the simple bending moment diagram won't be there. So only for the final end moments only, there will be a bending moment diagram. So this shaded portion is your final resultant bending moment diagram. So these are the references. Thank you.